Okay, so for question 5, well, basically, this one is asking you or testing you several areas of the knowledge. So, for example, how to write a Lewis structure, dotted Lewis structure. So, this is a very important topic. We have mentioned it again and again. And also study the atomic structure and the periodicity of the elements. Okay, so now let's have a look of these questions. The first one, well, basically you have a series of the metals and the formula of the compound, and here the students make a hypothesis. So this is a general method that we typically use in scientific investment. So we have a scientist, or here is a student, have the hypothesis, and then based on the hypothesis, so probably we can do some prediction, and then we can verify the hypothesis by using the experimental data that are collected. And then after that, and then we verify the hypothesis and improve the hypothesis. So see if the hypothesis can be verified by the experimental data very well, and then which means the hypothesis is a good hypothesis, and then we can accept it. However, sometimes during the experiment, then we find that the hypothesis is not that accurate or not perfect, and then we needed to do some modification to improve it. So, and then finally make it a better model or better hypothesis. So basically, this is the process of the scientific discovery. And so I hope that in the future, this concept will help you in the higher level of the study, especially when you are in a college and in a graduate school, especially in graduate school. So basically, this is what you are going to do the discoveries, and then to do the more creative, creative thing. So basically here, this is the idea of the student. So he has a hypothesis, and then what we are going to do is to verify the hypothesis. So the hypothesis is the number of fluorine atoms will bond to nonmetals always equals to 8 minus the number of the valence electron in the nonmetal items. So now let's check. So for question A, so what would the formula for the compound between the chlorine and the fluoride? So we have chlorine, and then we have fluoride. So based on this hypothesis, and then we know that should be 8 minus valence electron of chlorine, so that is 7. So in this case, so that is 1. So the formula should be CLF. So this is the answer for question A. So for question B, write the Lewis electron dot diagram for the molecule of the CLF3. So for this one, you need to familiar with the procedures of how to write the Lewis structure. So we have practice this before a lot. So here I want to go over with you again, because this is a very important topic. So here I give a star over here. So this is an important topic. And so first of all, we need to find out how many electrons, the total valence electrons that we have. So we know that fluorine has 7 electrons, and then for the fluorine, it also has 7 electrons. However, in the molecules, we have 3 fluorine, so that is 3 times 7. So totally in these molecules, we have 28 electrons, valence electrons, and that equals to, so that equals to, if we divide it by 2, that equals to 14 electron pair. So this is the first step, find out how many electron pairs outside. And the second step is draw the structure. So we know that chlorine will be the central atom, and then we have fluorine surrounded with that. So basically you draw the structure and then connect each of the atoms by using the single bond first. And then you arrange rest of the electrons around each of the atoms. And so the third step is structure, and then have the single bond single bond first, and then arrange the rest electrons. So then in this case, we know that in order to satisfy the octet rule, so each one has 8 electrons. So for fluorine, we have 8. So then you need one single bond and then 3 electron pair. So similarly, we repeat for each of the fluorine. So then after this, then you examine totally electron pair that you have used. So for each of the structure, so here, if I use a different color to highlight it. So for each of this unit, you can find out totally there are 1, 2, 3, 4, four electron pairs that you use. So you have 3 units, so totally you have 12 electron pair that has been used. However, we know that in this structure we have we have 14 pairs. So that means we still have 2 extra long pair. So we assign it with the chlorine. So basically this is the Lewis structure of this compound. And after you write it, and then you double check the number of the pairs of the electrons, and then make sure it is correct. So basically this is a procedure for you to write a Lewis structure dotted structure. So for the simpler molecules, so that would be easy. So you can just assign the electron pair. But if you have a complicated molecular, especially when you have relatively large numbers of the electron pairs, then you may want to use this method. So that help you systematically arrange the electron pairs or the bond, and so that you, well, basically it's easier for you to work with a more complicated system. So this is the second question. Lewis structure definitely is an important topic. So this is something that I hope that you can practice more, and then make sure that you 100% get to the point if there is a question on the Lewis structure. The next question, well, this is related with geometric, predictor of the geometric, and how the geometry will affect the physical property of the molecules. So the good thing is that, well, actually, it tells you the potential geometry of these molecules. But actually, what I require, from my point of view, I hope that you can memorize the geometries of the compounds. So we have a slide previously. So yeah, probably later on I can send it to you again. So depending on how many V's per pair that you have, and then you can determine the base models. Yeah, so probably because this is so important, so maybe I go over this one with you again. So this is we talked about this earlier. Molecular structure. Okay, so this slide. Yeah. So can you see my PowerPoint slides here? Yeah. Okay, great. Yeah, so this is a very important slide. So I hope that you can memorize this, because it summarizes the basic geometric models for the molecules at the different possible situations. So the first important thing, or the most important thing, is that you count how many V's per pair of the in the molecule structures. So you should know what is a VSEPR pair. So basically, VSEPR pair is you count each. Let me see, VSEPR. Okay, so you count each bond. It could be a single bond, a double bond, or triple bond, whatever the bond is. So each chemical bond as one VSEPR pair. So this is one point. Another point is that you count each lone pair as one VSEPR pair. So this is how to count the VSEPR pair. And then if you have two VSEPR pair, the basic geometric model is linear, and the bond angle between them is 180 degrees. And then if you have three VSEPR pair, and the basic model is a trigonal planar, and the bond angle is 120. And if you have a lone pair, so the base model, which means in each of the dots there is extra atoms of the group over there or atom over there. So this is the base model. However, if you have the lone pair instead of the extra atom, or in another word, you use a lone pair to replace the chemical bond here, and then you have the subsequent lone pair substitute. So for example, if you for the three VSEPR pair model and with a lone pair, then it's changed to band instead of the trigonal planar, and it's changed to the band models. And if you have four VSEPR pair, well, the base model is tetrahedral, and the bond angle is 109. Well, more accurately, is 109.5 degrees. And the lone pair substitute is if you have one lone pair, then it's changed to trigonal pyramidal, and if you have two pair, it changes to the band mode. So this model is super important, and I hope that you memorize it very well, and especially the bond angles 109 degrees. So from your previous experience, probably you already remember that you counted several of the questions that ask you the bond angles of the molecules. So this is a four VSEPR pair basic model. And if you have five VSEPR pair models, the structure, the basic structure will be trigonal bipyramidal. So it's more complicated. And then for the bond angles, so there are two types of the bond angles. So you should know what the bond angle is on the plane or is on the perpendicular positions. So respectively, they are 120 degree for the planar and 90 degrees for the perpendicular positions. And if the atom is replaced by the lone pair, and then you have the seesaw model. So basically, this is for the one lone pair. If you have two lone pair, and then it's the T-shape. And if you have three, then it's linear. And the other one is a six VSEPR pair. So the bond angle is 90 degrees for the six VSEPR pair, and then the subsequent model, including the square pyramidal, square planar, T-shape, and the linear. So this picture or this slide is very important, especially basically the first three for your level, but I think it's good for you to also remember the last two, especially if you want to participate in Olympia competitions. So this definitely will be very important. For that type of question, the focus is on asking 5 pair or 6 pair, but for AP test, probably is up to 5. Well, this is some information for you to know, but this slide is very important, and I'm going to send you this slide later on today after the class. So let's come back. So I have a students coming in. I need to approve it. Okay. So basically, this is the Lewis structure and the geometric shape of the molecules. So we know that if we count the Vesper pair, so then in this case, so totally we have 3 bonds and then two lone pair. So then we have 5 Vesper pair. We have 5 Vesper pair, and then so it could be. Well, so if we know from that slide, and then we know when there are 2 long electron pair, well, basically that is a T-shaped, so we can tell directly. However, here instead of that, well, basically this is make it less difficult for the question. So it gives you some phenomena of the physical properties. So they found that the molecule has dipole moment, and has a dipole moment, and then let you to decide which one is correct. Well, for the trigonal planar, well, basically that is on the same plane, so somewhat like this shape. So basically, this is a symmetric. This is a symmetric arrangement, and for the symmetric arrangement, well, basically the dipole can be cancelled out. The molecule will show as a nonpolar molecules. And experimental data find out this one has dipole moment. Well, actually, it tells us this is a T-shaped. So this is a non-symmetric shape. So then when you justify your answer, basically you can just explain from the symmetric of each of the model. So the answer is a T-shaped. So the next part. So I write down, probably I write down the key information here for you. Okay, so the key information here is so it would be it will be T-shaped because the structure is because the structure is okay. Yeah. So basically, this is for question C. For the next part, well, so this is to verify the hypothesis. So through the trend, where you can tell, probably you can guess that for these formulas for the chlorine, maybe you have ClF and then ClF3. So then how to explain this? Well, basically, from the atomic structure, where we can see that there is all the numbers of the fluorine attached with the central halogen atom, and also from the periodicity, then we can see that as the atomic number of the central halogen increases, the number of the fluorine also increased. So for the chlorine here, you have 2, and for bromine, then you have 3, and then for iodide, then you have 4. So these basically are the two trend or 2 hypotheses that we can include in the hypothesis. So the first one is the atomic structure. For the atomic structure, so this one will have the odd number of F atom. And the second one is from the periodicity. So basically with the increase of the central atom, and the number of F also increased. Yeah, so basically these are the two additional items that can be added into this hypothesis. So this is how to do the question 5. And the next one is well, so this one actually talking about a little bit of the polymer chemistry. I'm not sure if you have learned this in at school, but well, I can give you a very brief introductions of the polymer chemistry. So polymer, well, basically that is a very big, very giant molecules, and typically it has a very heavy molecular weight. And so how the molecule, how the polymer molecules is formed. So basically that is just like, it has a basic unit, and then it's just like a stencil or stamp. So just repeat again and again, repeat the unit again and again. So this is what we can see from here. So basically don't be scared by this complicated structure. So you see in the middle, so here is a parenthesis. So here you have the parenthesis, and then here is the number of the n. So basically this is the basic unit for these polymer molecules, and so that is for PP, and then for PVC, and then the basic model will be here, and then you see the number of the n. That just tells you that we repeat this basic unit structure again and again. So if you check the part before and after, or left or the right of this unit cell, and then you are going to see that it's exactly the same. So exactly same repeat. So if you want to expand the molecules, basically you just repeat it again. So this is how the polymer molecules being formed. So here, let's have a look at of the question. So we have two types of the polymers. One is PP, another one is PVC. So they were put in a container that has water, and then you find out one polymer sinks into the bottom, and the other one is floated on the top. So what does this mean? Well, actually, that tells you that the density of the polymer is different. So one is basically is lighter than water, so that it can float it above the water. Another one is heavier, the density is heavier than water, so it sinks at the bottom. So that's a difference. So when we see the question, here is a very important assumption that says the spacing between the polymer is similar. So it tells you that the space is same. So the most important thing that matters with the density is what? The weight, because we know that the density is related with the mass and the volume. So here, if we check the basic unit for these two molecules, and then we find out the only difference is here. For the PP, you have the methyl group, and then for the PVC, you have the chlorine item. So that is the only difference. And then if you compare the weight, the atomic weight for these two functional groups, and then you may realize that chlorine has a higher molecular weight, well, the atomic weight than the CH3 groups. So then in this case, and then we can decide the PVC, because this one is heavier, the PVC will sink in the water. So that is because the chlorine atom has a greater mass than the methyl group. Oh, by the way, so here is the format of answer the questions. So typically your answer will put the answer and then give the reason why, because what. So for example, yes, because what, no, because what, it's heavier because or something like that. So this is a format of answer the questions. So for the next one, the synthesis. So this one tells you how to synthesize the polymers. So typically when synthesis of polymers, so that involving the unsaturated bond. So for example, a double bond or the triple bond. So it tells you that the boiling point of liquid propane, the first one, is lower than the boiling point of the vinyl chloride. Okay, so when you see the boiling point or melting point or something like this, physical parameters, well, you should be alert or no, they are talking about the intermolecular force. So intermolecular force. So this one is also very, very important. So by now, I hope that you should be very comfortable to answer the questions related with the intermolecular force and then how they will affect the melting point and the boiling point. So here it tells you which one has a lower boiling point. So the lower boiling point, what does that mean? So basically that's equivalent to the lower intermolecular force. So then in this case, well, we need to compare the structure of these two molecules. So the only difference, well, we know that is here. And both of the molecules will actually, they have the dipole-dipole moment and also the London dispersion force. However, so for the vinyl chloride, it has a larger electron cloud and is much more easily to get polarized, and so that it has a higher dipole moment. So because of this reason, it has a higher London dispersion force. So the overall, the vinyl chloride will exhibit a higher intermolecular force, so that it gives you the higher boiling point. Well, so this is basically how to answer these questions. Yeah, so I have mentioned this before. So especially when you explain the London force, so you should talking about the polarization of the electron cloud. So this is a key word. So I write it here. So polarization of the electron cloud. So before that is because the vinyl, the chloride has a larger electron cloud. Okay. So for the next one, that is to determine the delta H of the experiment. So this one actually is very straightforward. So we already know the standard entropy of formation of each of the components. So then what we need to do is just to find out the difference between the sum of the delta HF of product and minus the sum of delta H of reactant. Oh yeah, another word in for the equations, that is the right side minus the left side. So you just plug in all the numbers in into these equations, and then you will find out. So for these reactions, so now we are doing. So for these reactions, we have 6 CO2, so that give you 6 times CO2 is minus 394, and then plus 6 of water, so water is minus 242, and then minus, so this is the product side. The reactant side, then we have 2 times CH3H6, so that is 21, and then plus 9 times oxygen, because we know oxygen is 0, so this is 0. So by solving this, and then we find the delta H is minus 3858 kilojoule per mole. Yeah, so basically this is a combustion. Well, basically this is a enthalpy evolved with these reactions. And so if we compare this number with the number we have if we compare the first and the second reactions, and then we find that the second reactions will produce more energies. So basically that is the 2 more of the propane will release more energy. So, well, basically this question is pretty straightforward and not that many tricks inside. So the next one is, well, actually it's related with the kinetics, the rate laws. So here is the reactions. And then we have a table of data. So we have different trials, and then we have the initial pressure, we have the volume, temperature, T-half. And okay, yeah, so because my screen is changed, so I want to know, can you see my iPad? Well, can you just use the speaker? Tell me, can you see my iPad?
Yeah, we can.
Yeah, can see it.
Okay. Yeah, so this is a very typical standard kinetic types of the question. So you have a different trials of the experiment, then you have the data collected in the experiment. Okay, so the first question is, it's said the reaction is first order, and then how do you know this is a first order? So from our last lecture, we know that for the first order there are 2 characteristics. The first characteristic is there is a linear relationship between the log concentration and the time. So there is a linear relationship. So this is the first characteristic. The second one is it has a constant T-half, or in another word, the T-half through the experiment will be same. So let's examine the data that we have here. So we notice that the T-half here, so it is 100 seconds. So that satisfies the constant T-half. So through this data, then we can verify that this reaction is a first order reaction. So this is how to find out. Well, basically, no matter from which angles the question will ask you, so you need to to explain and then know the relationship between them. So if you know it's first order, and then you can predict the linear relationship between the log concentration and the T, and also the constant, it has a constant T-half. Or if you know one of them on the left side, and then you can predict this is a first order reaction. So this is something that you should be very familiar with and also memorize very well, and also know how to use it flexibly. For the second question, calculate the rate constant. Then in this case, well, for the first order reactions, we know that the K equals to log 2 divided by T-half. So this is the equation that you should memorize. I know this equation will be given from the factor sheet at the beginning, but this is something that I want you to memorize, to remember. So through by using this equation, we can figure out what is K for these first order reactions. So natural log of 2 equals to 0.693, and then we know T half equals to 100 seconds. So the result is this number, and don't forget the unit. So that is S minus reciprocal of second. So yeah, including the proper unit. It's very nice that they remind you to including the unit, but this should be a habit. When you calculate the K, you should always come along with a proper unit after your calculation, even though they didn't mention that you should have the unit. So this is something that you should know. So for the next one, is the initial rate of the reaction in trial 1 greater or less than the trial 2? Okay, so then let's check trial 1 and trial 2. So these two experiments. So we find out for these two sets of the experiment, so everything is the same. So V, T, and T half is same. The only thing different is the initial partial pressure for the reactant. So trial 2 will has higher pressure, or in another word, higher concentrations. So then in this case, we can predict that trial 1 actually is less than, the rate is less than trial 2. It's because trial 1 has the lower partial pressure than the trial 2. Well, actually behind that, actually it is because of the concentration is less. So well, this is also a very typical question. So you should answer like it is less than, because of whatever reason. So this is a question C, and then for the last question, so let's compare the trial 4 and the trial 1 and then see what happens. So for trial 1 and the trial 4, and then we find out the initial pressure or initial concentration is the same. However, the volume is the same. However, the T is different. The trial 4 has higher temperature, and that also resulting in you have a different T half. So the question is, the half time of trial 4 is less than half time of trial 1. Is why in terms of activation energy. Well, so what happens when you have a higher temperature in the gases reactions? So we have discussed this before. So when we have a higher temperature, so that means the average kinetic energy of the molecules is also higher, also greater. So as a result, consequently, so this, well, the trial 4 has a greater fractions of the collisions, has a sufficient energy that can overcome the activation and energy barrier. So that the rate is faster, and well, because the rate is faster, so the T half will be shorter, right? So this is also a very important conclusion that you should be very familiar with. I write down it here, so I hope that you can be very familiar with this paragraph of the words, because you can apply this to other places, or apply it to the similar scenarios types of the question. So with the higher temperature, the higher temp. So this is D. Okay. The temperature in trial 4 is higher. Higher. So which means, so that means you have the higher, the average kinetic energy of the molecule is higher. Maybe it's greater. Okay, So when you have a greater average kinetic energy, so that means so consequently a greater fraction of collisions have sufficient energy to overcome the activation energy barrier, and thus the greater is greater. Okay. Yeah. So basically, this is like a general explanation for this type of these questions. So if we go to the question that we have worked before, and then you are going to see the similarities. So okay, yeah. So this is the next that we are going to do. So do you still remember this one? This question? We have go over that before, probably like more than 1 month ago. Do you remember this question? So this, if you look at the question here, the B, the first question in B. So at a 30 Celsius degree, the reaction is thermodynamically favorable, but no reaction is observed to occur. However, at 120 Celsius degree, the reaction occurs at a observable rate, and then explain how the higher temperature will affect the collision between the reactant molecule and that will basically at the different temperatures. So this is exactly the same types of the question. So basically you should will answer in the same way. So at a higher temperature, you have the higher average kinetic energy. So larger fractions of the molecules will have the sufficient energy to overcome the activation energy barrier, energy, so that you have the greater reaction rate. So when you have greater reaction rate, and then you have a smaller T-half, right? And so if you want to visualize this from the activation profile, and then you can see this is the energy barrier of activation energy. And then so that can also help you to understand what happens here. So basically, this is how to address the question, this type of the question. So the purpose is not that you know how to solve one problem. The purpose is to, when we do this practice, we want you to learn the knowledge and then learn how to apply the knowledge to solve the same types of the questions. Okay, so the 2017 questions we have go over before for the question 1. So now I'm going to start with the question 2. So for question 2, well, this one talking about a new knowledge. I mentioned that before, but I didn't emphasize it very much. So what's that? So that is a formal charge. Okay, so let's examine this question first. So let's read it together and then examine this question first. So basically here you have two molecules, and then it gives you the Lewis structure of these two molecules. So basically they contain the same molecular formula. However, there are two possible ways to write the Lewis structure, and both is okay, acceptable. If you examine them, both are right. So, however, the diagram on the left is better representation for the bonding in formic acid, and the reason why. So it asks you to justify your choice based on the formal charge. Okay, so now I'm just we'll spend. I think we should spend some time to talking about the formal charge. So for the formal charge, that will basically you can understand that it's like an assigned charge for the molecules. So how to calculate the formal charge? So the formal charge equals to the number of valence electron, the total numbers of the valence electron, minus 1/2 of the bonded electron, and then minus the number of the unshared electron, or the lone pair electrons. Either way is okay. So here we have the two Lewis structure. Well, so in order to find out the formal charge, and then you need to write the Lewis structure first. So we do that side by side. So for the first one, the Lewis structure is like this. And for the second molecule, the Lewis structure is like okay. So now what we needed to do is to figure out the formal charge for the atoms. So on the left side, let's check the oxygen. We know that the oxygen total number of valence electron of oxygen is 6, and the minus half of the bonded electron. So it has a one single bond, so that is 1/2 times 2, and the minus the unshared of the electrons, or the so then in this case we have 6 unshared electrons totally. So that one gives us the formal charge for oxygen is -1. So I put -1 here. And for the nitrogen, similarly, the nitrogen, the total valence electron is 5, and then we minus 1/2 of. So it has the 3, where all the electrons actually are shared. So then that is 1/2 times 8. So that one gives you 1. So for the nitrogen, it's +1. And for the carbon, so we know carbon has 4 valence electron, and the minus 1/2 times 8. And that gives you, oh, sorry, why I put 2 dotted here. So that gives you a formal charge of 0. So for the hydrogen here, well, basically that is 2 minus, sorry. One minus 1/2 times 2, that is also equals to 0. So similarly, we are going to find out the formal charge for the molecules on the right side. So the oxygen is similarly 6 times 1/2 times 4, because here you have two double bond. So you have 4 electrons for the double bond, and the -4, so that one give you 0. So this one is 0. And nitrogen, similarly, 5 minus 4 equals to 1. And the carbon, that is 4 minus, so I put a dotted here. So this one has only 1. Okay. 3, and then -2, so that one equals to -1, and the hydrogen is 0, 2. Okay, so now we check the formal charge of the right side. So then we find out, well, basically now we find out the formal charge, and then we compare these molecules, and then see the see the similarity and the difference. We find out the difference actually is the formal charge of carbon and oxygen. And so here on the left side, carbon has 0 formal charge, nitrogen has -1. On the right side, carbon is -1 and the oxygen is 0. So when we compare, actually, the way it's better to put the negative formal charge on oxygen. It's better than on the carbon is because oxygen is more electronegative than the carbon. So basically, well, it's better to let the oxygen to carry the negative charge. So this is the reason why the structure in the left side is better represented on the right side. So this is how to explain from the formal charge point of view to these questions. Yeah, so this is part A, and then for part B, also talking about the Lewis structures, and but the question is determine the value of the delta H for the reactions. So basically this is to determine the delta H from the bound energy. So for this type of the question, also the first step is to find out the Lewis structure, and the second step is to figure out how many specific bond in each of the molecules, and then after that, then you can do the calculations. So I will just write it down here. So for the reaction involved here, I write it. So instead of using the molecular form, I'm going to use the Lewis structure. So for the Lewis structure on the formic acid, so that is HC. So yeah, so this is a reactant, and then our product is this one. So let's examine how many chemical bonds that in each of the molecules. In the reactant, so we have one CH bond, we have one triple bond, and then we have another nitrogen oxygen single bond. And for the product, so then we have one single bond, so that is H and between H and N, and we have a double bond between nitrogen and carbon, and a double bond between carbon and oxygen. So we listed all the chemical bonds in the molecules, and then the delta H equals to the sum of the delta H of the bond broken and energy involved in bond broken, and minus the sigma of the delta H involved in the bond formation, bond formed. Or in another word, so in this case, so that is the left side minus the right side. So in a lot of the calculation of the delta H is always the right side minus the left side, but for this one, involve the bond energy is left minus the right. So that gives you the sum. So that is the sum of the bond energy for the reactant. So that is 413 plus 891, and then plus 201 minus okay. So then we get all these numbers from the table that we have here. So for example, for carbon hydrogen single bond, it is here. So 413, and for the triple bond carbon nitrogen triple bond, so that is here. So and for the nitrogen oxygen single bond, it is here. So basically, you find out the all the bond energy in the reactant part. And similarly, you can find the bond energy for all the bond involved in the product. So the result is minus 246 kilojoule per mole. So this is how to find out the delta H for this reaction. The next question is that the students claim delta S for this reaction is close to 0 and explain the why, the reason why. So we know that during these reactions, if we check the molecules, basically it's just the change for this change is a rearrange of the atom. So this is only a rearrange of atoms. So there is no phase change, and then there is no change of the number of the molecules. So there is no change of phase or the number of molecules. So because of this reason, and then we can predict that the delta S is close to 0. Because typically when the delta S is changed, it's due to, for example, there is a change of the phase. For example, if you change from solid to gas, or from the liquid to gas, so the delta S will increase. Or if you have the increased number of the molecules, the delta S will also change. So this is part C. And for part D, which species is represented in a higher concentration at 298 K. So for this one, we need to figure out, do a little bit of calculation to predict which one is higher. So in these reactions, we already know delta H. We also know delta S is roughly equals to 0. So we can calculate delta G. So delta G equals to delta H minus T times delta S. So then the delta H we find from the calculation here is minus 246 kilojoule per mole, and the other part is 0. So that is a kilojoule per mole. So you can see that the delta G is a negative number, and a pretty big negative number. So then we know that thermodynamically it's a favorable the reaction. And if we want to calculate the K, so we know that the delta G equals to minus RT log K, and then we know this one is a negative number, and then we can find out actually the log K is a positive number, and actually it's a pretty big number after your calculation. So that is roughly equals to 99. So from such a big K number, and then we know that the reaction is favored to the forward reaction. So then in this case, the product, the isocyanic acid, will be has a higher concentration. So typically this one, if you just explain which one is favored of spontaneous reactions, so then you can tell which one has a higher concentration. So for the next question here, it gives you the information of the decomposition of urea. So this is a kind of fertilizer, very commonly used. And the next question is the kinetic. Okay, so here, still similarly, we have a set of the data obtained from the experiment, and also we have a plot, we have a curve of the process. So, actually this one will be very straightforward for you right now. So for question E, the students propose the reaction, the rate of the reaction. So from the rate law, what can we tell? Which order? Okay, so from the rate law, it is a first order reaction, right? So because the exponent here is 1. So the first question is how the data support the student proposed the rate law. So we know that this is a first order reaction, and which kind of the data we can use. So we already know that for the first order reaction, one is a linear relationship between the ln A and T. Another one is a constant T half, right? So then in this case, because we have the plot, we have the plot here. So this give you the concentration instead of the log of the concentration. So it's not that straightforward to see, but we can compare the T half, right? So this requires you the ability to read the chart. So we know the initial concentration is 0.1, and then the T half corresponding the concentration of 0.05. So, and then we can find out the T half from the curve. So that is 10 minutes. So the second T half, so that is a change from 0.05 to 0.025. So this is a little bit like here. So from the curve, you can read the T half is changed from 10 to 20, so it's another 10 minutes. So then in this case, you know that the T half equals to 10 minutes in this process. So the constant T half actually support the proposed rate law is the first order reactions. Okay, so this is how to do the first question. The second question, using the proposed rate law and the student's result determine the value of the risk constant K. So still again, so right now this is just a too simple question for us. So we know K equals to Ln K divided by T half, right? So that we can find out the K. So that equals to divided by 10. However, the unit here is we needed to be consistent with the unit. So it's hour instead of second before. So that is 0.0693 hours minus. Okay, so this is the unit. So for question F, yeah, the students learn the decomposition run in a solution with a pH of 13, and then briefly describe an experiment, including the initial conditions you should change and the data you would collect to determine whether the rate of the reaction depends on the concentration of hydroxide ions. So this actually is a challenging, but it's a very good question. Why it's challenging? Because that really needs your real understanding of the experiment on the process, how things going. Or in another word, this is like an experimental design type of the question. So I would give it a star. So this is a very good question. That really needs your like a higher level of the thinking. So in order to, or in another word, you can interpret this question as how is the effect of the how is the effect of hydroxide concentration on the reaction, or how the change of the hydroxide concentration will affect the reactions. So then in this case, when you need to design an experiment, when you need to design an experiment, what you need to do is that you keep the hydroxide ion or the parameters that you are interested in as the variables. So this is your variables. And then, well, you still measure the rate of the reaction. However, you keep all the other conditions or all the other parameters unchanged or the constant. So in this case, any change from the concentration will be reflected from the change of the rate. So through this way, well, actually, you are going to be able to tell if changing of the pH or changing of the hydroxide concentration will affect the reaction or not. Well, so this basically is how to design this experiment. You can perform the experiment at a different concentration of the hydroxide and measure how the concentration of the urea will change over the time. Or in another word, how the reaction proceeds. So all the other variables should be keep constant, no change. Yeah, so this is question F. I hope that you can think a little bit more, really digest the question F afterwards. So the next question is, yeah, this one actually involves the several of the topics. One is the equilibrium, another one is acid-base, and also topic in the buffers. So for the first one, write the expression of the equilibrium constant for the forward reactions, so Kp. So this one is straightforward. The Kp equals to, because these are the gas, so then you're using the partial pressure to find out the Kp. So that is the partial pressure of NO. However, because you have the two coefficient 2, so here you should have square, and then divided by the partial pressure of nitrogen and times partial pressure of O2. So this is how to find out the Kp of the solutions. Of the reactions. So for the second question, if let's examine that. So the students inject the N2 and O2 into a, here is a keyword, previously evacuated rigid vessel. So which means it's an empty vessel before, and then start the reactions. And the initial partial pressure, so you know the initial partial pressure. And then the system, then the reaction will start happen, and then the system is allowed to reach equilibrium. And after that, you measure the partial pressure of the product is 0.122 atm. So you know the equilibrium pressure of the product, and then calculate the value of the P. So we already know how to calculate the equation of the Kp. So what we need to find out is the equilibrium pressures for each of the components in the system. So for this one, actually, you need a little bit of the calculation using the ice table. So here you have N2 plus O2, and then give you 2NO. And so initially, we know that the pressure of N2 is 6.01, O2 is 1.61, and then the change and the equilibrium. So for change, we are not sure right now, but we do know the equilibrium pressure for the product is 0.122 atm. So this is the equilibrium. And then we know the equilibrium of the product must coming from the reactions. So basically the change is 0.122. So because we know the initial concentration, initial pressure for the product is 0. So now we know the change of the product, so we can find out the change of the reactant. So if we examine that, we find that the ratio between them is 1 to 2. So when you generate 0.122 product, so which means you consume half of this much amount of the reactant. So that equals to 0.061 oxygen and similar 0.061 nitrogen. So now we know the initial, we know the change, and then we can calculate the equilibrium. So the equilibrium pressure for N2 equals to the difference. So that is 5.949. And the other one is 1.549. So now we know the equilibrium pressure for each of the components. So we just put into the equations the Kp. So that is PNO square over N2 and then PO2. So that gives you 0.122 square and divided by 5.949 times 1.549, and then that gives you a final answer, number of 1.6 times 10 to minus 3. So this is the Kp for the reactions. So this is the the second question. So the next question. So question A and question B, so that is in the topic of the equilibrium. So you should know how to calculate the equilibrium constant based on the experimental data. So the following part will be in the acid-base chapter. So I probably just go over that very quickly for the rest of the part. For question C, well, basically the students asked to make a buffer solution by using the acid and the hydroxide solutions. So for the buffer solution, we're typically that including a mixture of the conjugate acid and the base. So that is a key component of the buffer. So you need to have a conjugate acid and base in a buffer. So then in this case, for the conjugate acid, then we know we have acid. So that is HNO2. And how to get its conjugate base? So we know that its conjugate base is when it loses a proton. So it's a NO2 minus. So then how to do that? Well, basically that is because of the neutralization reactions happens between the acid and the base. So we know that there is a neutralization reaction between the acid and the sodium hydroxide. So that gives you the sodium nitrite and water. Okay. So basically, this is a chemical neutralization reaction happens in the system. So through the reaction, we can obtain the conjugate base. So the first question ask you to using the net ionic equations for the reaction. So here, this is a neutralization reaction. So this is the actual chemical reaction happens in the system, but we can basically simplify that into ionic equations. So the ionic equations here will be the weak acid. So weak acid you have to write as a formula because weak acid is only partially dissociated. So here we just think it is undissociated. So it has to be in the volume the molecule form, and then plus hydroxide ions, and then that gives you the conjugate base and plus water. So this is the ionic equations involved in this process. So for the second part, determine the volume the students should add into to this solution to make a buffer with a pH of 3.40. So for the buffer systems, so you need to be very familiar with the equation, which is Heisenberg equations. So that is the pH of the solution equals to pKa plus log base, conjugated base over acid. So this is an extremely important equations. But it's not going to be covered by this AP exam, but I don't know if you're going to have chemistry exam in your school, but this is a very, very, very important equations. That is something you should memorize very well. So then we know that pKa for this acid is 3.4. And if you want to prepare a buffer solution, also has a pH equals to 3.4. So what does that mean? So which means actually the log, so the second part equals to 0. So when this part equals to 0, so that happens when your plus log A minus over HA. So when that happens, the concentration is the same for these two components. So it could be the concentration, or it could be the number of the moles of the two components. Because in the solutions, they are in the same buffer solutions, the volume will be same. So if you have the same number of the moles of the component, that equals to the same concentrations. So basically, this is a condition that you need to satisfy in order to prepare buffer solution with the pH equals to the pKa. So then in this case, we'll actually we can just calculate how much total acid, initially acid that we have, and then you cut half, make it to the conjugate base. So then in this case, what we have is totally the acid equals to 0.1 liter and then times 0.1 m, so that equals to 0.01 mole, and the half of that is so half of that so is 0.01 divided by 2 equals to 0.005 moles reacted. So you need this much of so this is reacted. That also equals to the amount of the sodium hydroxide. So the we know that so that equals to the amount of number of moles of sodium hydroxide. So the sodium hydroxide equals the volume of the sodium hydroxide equals to 0.005 mole divided by the concentration is 0.1 m. So that gives you 0.05 liter. So that is 50 milliliter. So basically, the answers for this one is 50 milliliter. 50 milliliter of the sodium hydroxide needed to be added. So for question D, a second student prepare a buffer, but I think by using a different way. So you may notice that the second student will actually using higher, well, basically in the system, you have a higher concentration of the conjugate pair. So this one can be get from the simple calculation. So in the second student, it has 0.1 more of the conjugate base and 0.1 more of the acid. So even though the ratio between them is still 1:1, so you get the same pH. However, because the second student in the system, buffer system, containing more amount of the species or substance, so it has a higher required buffer capacity. So so basically, this is the reason why it is a more resistance to the change in the pH. The more resistance change to the pH, which equals to the higher buffer capacity. Okay. So the next question, it give you a diagram, give you a figure, and then ask you how the pH is. So for this one, then you need to count how many acid you have and how many number of the conjugate base that you have. So here I use probably I use a different color to make it easier to see. Okay, so then in this diagram, and then you count for the acid, you have how many numbers? So you count 1, 2, 3, 4, 5, 6. Okay, so totally you have 10 molecules, and for the conjugate base, you have 5. So this is 1, 2, 3, 4, 5. Okay, you have number of 5. So again, you plug it in to these equations, and pH equals to pKa plus log A over HA. So then you know that conjugate base equals to 5 and acid equals to 10. So basically that is 1/2. So by solving this equation, then you know pKa is 0.4, and then plus log 0.5. So that gives you a final reading of 3.09. So basically that is the pH of the of this buffer. So if we compare the pH, well, we know that this is less than 3.4. So the reason is because of this reason. Okay. Yeah. So this is how to answer the question E. Okay, so the next question is a thin layer chromatography or the paper chromatography. So before I proceed to answer these questions, probably I needed to give you a very brief lectures of this topic. This is a very important topic in separations, analytical separations. So then I'm going to share you the screen with. Okay. I'm going to share you the screen with this one. Okay. So now I'm in a PowerPoint slide. It shows thin layer chromatography. So can everyone see these slides? You just speak and.
Yes.
Yes. Okay. Okay. Good. So, well, thin layer chromatography belongs to a very important analytical separation technique. So paper chromatography is part of them. So here for the thin layer, well, it could be, well, for the separations, this type of the separations, we should understand it has two phases. One we call it is a stationary phase, another one is the mobile phase. So mobile phase, well, typically is our solvent. And the stationary phase, it could be like a paper, and it could be the chemical species or the components coated on the piece of like a plastic or the most frequently we use glass or glass plate. So then in your case, what you should understand is you have a piece of paper. The paper, it serves as a stationary phase. And you have the mobile phase. The mobile phase is the solvent or the solvent mixture. So basically the separation happens between the distribution of your analyte between the stationary phase and the mobile phase. Or you can understand its distribution between the paper and the solvents. So because of the different affinity or the molecular interactions between the analyte and your mobile phase and the stationary phase, so the migration speed of the molecules along the paper will be different. So when we started to do the analysis, we apply all the components at the same starting point. And then after that, we develop the paper. So it's just like a race, like a 100-meter race. So everyone starts from the same starting point. However, different people has a different running speed. So they are going to take a different time to reach the end point. Or in another word, if you give them the same time, they are going to run the different distance. So that is the idea of the paper chromatographies. So we are going to examine how fast the people or the analyte travels along the paper, so that we can separate them and then using the information to identify them. So in this technique, typically we include 3 steps. The first step is the sample application. You apply your sample to the paper to the starting point, or it's like the athlete, everyone get ready at the starting point. So this is the first step. The second step is the plate development. So that is start to run. So equivalently, that means we put the paper or the plate into the solvent chamber, and then let the molecules run along the paper. And finally, we needed to do the detection to find out where they are. So quickly, very quickly. So for example, if you have a piece of the paper, if you want to run the paper chromatography, and then typically this is a rectangular shape of the paper, and then you use a pencil, very lightly draw a straight line at the bottom. So the distance is roughly like 1 to 2 centimeter. And then you put a slightly point, like a cross here. So it tells you where do you apply your samples. So the purpose is to make sure that you apply your samples uniformly at the starting point. So after that, after apply the sample into the starting dots, and then you put it into a development chamber. So this is how the plate development chamber look like. So if you have a glass plate, then you can put it inside. And then if you have a piece of paper, probably it's not going to stand by itself, and then you may have the rack or something to hold it. But the point is that you immerse this part, the part below the line into the solvent. However, your solvent line cannot go above this pencil line that you draw. It has to be lower than that. And then when this paper immersed in the solvent, and because of the capillary fractions, the solvent will start to climb up along the paper, and then when it reaches the starting line, it's going to carry the analyte, carry your samples, and carry it moving upward along the paper. Because of the different affinities of the analyte to the paper and to the solvent, so it's going to travel at a different speed. So over some certain time, you are going to find out they are going to show up at the different places, somewhat like here. So then after you develop, we call it the plate development. After you that is run, and finally at last, then you are going to do the sample detections. Basically, you are going to visualize where the spot is. So for the paper chromatography, or for your level, most likely you are going to be given a colored species, for example, the food dye or something like that. But in a lot of majority of the applications, well, your analyte actually is invisible. It doesn't carry color at all. So then in this case, you need to apply some reagent to visualize, to make it to be seen. So you can spray a visualization reagent to let your analyte spot show up on the paper, or you can examine the plate under a UV light, special light, so that you can visualize that. But no matter what, you need to know where your spot end up with. So this figure here show a very typical we call it a chromatogram obtained through the thin layer chromatography or the paper chromatographies. So let's have a closer look at this. This is very important. And this is also what the AP question asked you in next question. Okay, so then you examine this piece of the paper. So here you have the starting point. So this is the original line. So this is a pencil line that we draw at the very beginning. And then here you have sample 1 and sample 2. So this is your starting point. So previously we draw two cross here. And then after the plate development, or after you put the paper chromatography in the solvent, you notice that your analyte will actually migrate or travel along the paper. And by the end, then you find out, for example, the sample 2 end up here in this place, and the sample 1 will actually, it has two analyte. This is a mixture, so it end up to the smaller dots and the bigger dots here. It's labeled as WB and WA here. Then you'll notice that these 3 dots actually travel different distance at the given time. And there is another thing that, another thing that you should notice is the solvent front. So this is how the distance that the solvent climb up along the paper or travels. So we are going to measure several of the distance. So that is very important for us to do the next step analysis. So the first one is the distance between the original line, the pencil line that you draw, and the solvent front. So this distance, we call it dm, the solvent front line, dm. This is the first thing that you should measure. So you can use a ruler. During the experiment, you can just use a ruler to measure, find out the distance. For example, it's a 6 centimeter or something like that. And the second thing that you should measure is the distance of the analyte travels. So that is the distance between your starting line and the spots. So here we label it as dr. So dr is the distance between the starting line and the final spots of your analyte. And then we are going to calculate, and then we introduce a factor which is called retardation factor, Rf. The Rf value is a characteristic value of a given chromatographic system. So this is a very important factor, the Rf. So the Rf, by definition, the Rf equals to dr over dm, or the distance, the ratio between the distance, dr over the distance of the solvent front travels. So this is the Rf values. For the given system, if you have the exactly same separation conditions, especially when you put your standard analyte and your unknown analyte in the same plate, so all the other parameters are consistent. The only different thing is the distance, the drs. So you can use this information to determine what your unknown is through this comparison, and or through the compare of the calculation of the dr, if that is developed in two different experiments. So the Rf value is a characteristic value of the given compound at a given conditions. So this is some kind of like a constant, but that is heavily depends on your experimental conditions. Okay, so then after that, we are going to calculate the Rf values and then identify the potential candidates. So in the most cases in the reality in the lab, well, actually this technique is a traditional technique used to determine marijuana in a crime lab. So well, basically they just develop the plate and then compare the spot with the standards. So we can run the unknown and the standards in the same plate and compare the spot position. So this is the most typical way that we do that. But if you want to do more advanced technique, so we can run the test by using the UV, IR, or mass spec. Well, basically this is beyond your level right now. Okay, so what you should know is understand the paper chromatography, how it look like, and understand the DR, DM, and also the RF. So for AP test, I think this should be good enough. Okay, so this is what I want to mention for the paper chromatography. So now let's come back to see our next question. Is this a problem? I can't. Okay, let me do it again. Share. Yeah, it looks there's some communication issues between my iPad and the Zoom. Okay. Okay, good. Okay, paper chromatographies. So so now I think you should have a good understanding of what the paper chromatography is and then how to interpret the data. Okay, so for the question A, well, basically in this system, you have three standards. So that is by ABC, three colored species, and you have one unknown. And then the solvent, you're using the nonpolar solvent. So this is a mobile phase. And the first question is, which dye ABC is the least polar? Is the So in order to understand these questions, well, basically you need to check the how far the dye that moves along the paper. So then you should understand in this way. Well, so it follow principle like dissolve like dissolve like. So the analyte or the dye can only move when it dissolves in the mobile phase. So if you have a nonpolar solvent, so which means nonpolar components like nonpolar solvents. So, or in another word, the nonpolar analyte will have the higher solubility in the mobile phase, so that it can travel along with the solvent in a faster speed compared with the polar analyte. So then in this case, and then we can find out if we check the dye C actually travel fast. So then in this case, we know that the C is least polar. So basically is the most non-polar. So that equals to least polar. So when you answer this question, and then you can just answer in this way. And so this is our typical format. Give the answer and then give the because. So you can just answer that the dye C is the least polar because it moves the fastest. Because the nonpolar dye are more strongly attached to the nonpolar solvents. So this is the reason why. So maybe I write the because here. So this is because nonpolar dyes nonpolar dyes are more strongly attract to the nonpolar solvent. Okay. So for the next question, which dye is present in the unknown samples? So typically this is the purpose of the paper chromatographic analysis, find out the unknown. So it looks like if you check the standard is one and the unknown, it looks like they are developed in different trials because they have a different solvent front. However, well, so typically this is a non-typical experiment, but typically what we are going to have is we have a piece of the paper, and then so this is the original line. So we have this, we have different standards. So we have standards 1, well, for example, standards 2 and standard 3, and also we have an unknown. So this is when we apply the analyze to the paper, and after development, what we are going to have is after the development, what we are going to have is the same piece of the paper. So we have this is a original line. and then we have the solvent line, the same solvent line. So this is the solvent. This is and then you are going to find out the first one probably travel this much, the second one travel this much, and the third one maybe travel this much, just pretend. And for your unknown, maybe it's here. So by checking the positions, and then you are going to know that the yellow and the, well, basically these two are on the same level. So then you know that you are, let's see the, let's say this is A. So this is A, B, C, and unknown. And then from this comparison, and then you can see this is A, B, and C. This is your unknown. So then you can tell your unknown equals to B. So this is a typical experiment. But the question that give us here is not a typical experiment. So they developed from the different trials. So then in this case, what you needed to do is to compare the RF values. So you remember the RF, how to calculate the RF, right? So the RF is you're using the distance of the solvent, of the compounds that moved, and then over the distance of the mobile phase. So then here, basically you need to like an estimation. So your data point is here. So the distance that moved, this is a dr, and then this is a dm. So then in this case, the RF probably like roughly equals to 0.5. So this is just an estimation. And similarly, then you are going to do the estimation for the for the standards, and then you are going to find out for the die A has a, so this is a distance of A traveled, and then this is a front line. So this is a dm prime. This is a dA probably. So the RF value of A is also roughly like 0.5. So then in this case, then you can, so now let's come back. So for question 5, let's see the first part. Then we need to find out the the heat evolved in this combustion process. So for this one, I can just use the equation of, I write here, so this is for part. For question A, so the Q, the heat evolved in this process equals to mc delta T. And then we can find out all the information on the table we have. So the total mass is 125.00 gram, and the specific heat of the water is 4.18 joule per gram, and the Celsius degree, and the temperature, difference of the temperature is we use the final temperature minus the initial temperature, 51.1 minus 22.0 degrees. So this is the gram. So by solving this equation, and then we can find out the Q equals to 15.2 kilojoule. So you have to be aware of the what's that, the significant numbers in this type of the calculations. So this is how to find out the heat energy for question A. For part B, based on the experimental data, and how much how much is 1 mole of the propanol be combusted. So from the experimental data, we know that the mass of the fuel or the propanol evolved in this process is 0.55 grams. So This one is only small, very small amount. So then we can find out how much number of the moles of the propanol involved in this process. So that is 0.55 gram divided by the molecular weight of the propanol. So the molecular weight of the propanol equals to 60. Equals to 60. So then you divide it by the molecular weight, so that gives you the number of mole is 9.166 times 10 to -3 mole. So this is how much of the mole combusted in this case, but we needed to convert it to 1 mole. So for the 1 mole, we know that should be 15.2 kilojoule divided by 9.166 times 10 to the -3 mole. So that gives you a final reading of 1.7 times 10 to 3 kilojoule per mole. So this is for the part B, and for part C, the second student performed the experiment using the same mass of the water, however, for the propanol, it's contaminated with water. So water is miscible. Basically, it has a good solubility in alcohol. Because both of them are the polar solvents. So if you use the same amount of the contaminated propanol, so then we can imagine that during the combustions, the total heat released will be less than the pure solvent. So then in this case, the answer is the final temperature will be less than the first experiment. It is because the actual amount of propanol involved in this experiment is less than the first experiment. So because you release less energy, so the temperature of the water, that the final temperature of the water will also will be lower. Yeah, so this question actually is pretty straightforward. It's not complicated at all. Okay. And then we are going to have another one. So this question, question 6. Okay. So question 6 is something that you should pay attention to. So this is a question that I hope that you can spend some time after the class to make sure that you understand it very well. So this is a question should belong to the topic of the equilibrium, and also this is a question associated with solubility product constant, the KSP. So this is similar to like acid base. This is a very important topic, but this will be covered by the current AP exam. So we have a system. So basically, in the question with related to the KSP, the first step, no matter what my suggestion, the first step is to write it down, the dissociation, the equilibrium. So then we know that it's going to the solid will dissolve in the water to give you the ions, metal ions, and also basically the cation and anions. So just imagine this is a very critical, very general equations. So basically, you write down the ion equations, and then let's check the question A. Calculate the number of the grams that dissolve in 100 milliliters of the saturated of the solution. So what does saturated solution mean here? So basically, that tells you that you well, basically the precipitate or the solid has released some of the ions, and then it reach a saturation solution. This saturated concentration actually equals to its solubility. So, or in another word, this one is asking you to find out the solubility of your compound. So they just asking from the different way, but what you should know is, well, it's actually asking you what is the solubility of your compound. So then in this case, we'll calculate the solubility. We can assume the solubility of the compound is X. So this is X, and then we can produce the same amount of the cation here, and also the 2 times of the anion here. And for the KSP, we know that equals to, so this is a solid, this is the aqueous, this is in the aqueous, and then this equals to, so this is the first step, find the chemical, write the chemical equations, and the second step to write the KSP. So this is the KSP, and make sure that the exponent equals to the coefficient in front of each of the species. So, well, basically you don't include the X here because this is in the solid form. You plug it in, the X, into this equation. So here you have X and then times the 2X, but you need to have a parenthesis and then square, because this 2X is the concentration of the hydroxide. And you should have the square of the total concentration of the hydroxide. So you need to put a parenthesis. Sometimes the students don't put a parenthesis. So basically they just partially square of the 2X. So still that is not correct. So then that equals to X times 4X squared. That gives you the 4X cubed and equals to KSP. So the KSP is 1.8 times 10 to minus 11. So by solving this equation, well, actually you can find out the X, or the concentration, that equals to 1.65 times 10 to minus 4 m. So typically the concentration used associated with the KSP is molarity concentration, so that is M. So now we know the concentrations. Well, the next step is to find out how much of the grams dissolved in 100 milliliters of the solutions. So we know the concentration, so it's 1.65 times 10 to minus 4 molarity, and then we want to figure out how many number of the moles in 100 milliliter of the solution. So then you times 0.1. So this is the number of the moles, and also so that gives you the 1.65 times 10 to minus 5 mole of the solute that you have in the solution. In order to find out the grams, and then we need to times the molecular weight of the solute. So that is 58.32 grams per mole. So this is a mole. And then it gives you 9.6 times 10 to minus 4 gram. So basically, this is how much of the gram of the solute has been found in this saturated solution. Well, here, in order to make you easier to see or easy to understand, I separate into 2 steps. But actually, if you are familiar with with this, and then actually you can combine these two steps together and then give out the number of the gram directly. Okay, so this is question A, and then for question B, well, it's talking about the lattice energy. So when we are talking about lattice energy, and then we need to also think about the electrostatic attraction force. And also we need to know that it's related with two important factors. The first of the factor is the Q, the charge of the species that carried, and the second important factor is the R, of the distance. So basically, these are the important information that you should you should know. So for the lattice energy, so then you should understand from the electrostatic force. Well, typically, when there is a higher force, higher electrostatic force, well, basically that correspondent to the higher lattice energy. And so for the electrostatic force, well, basically we needed to very familiar with Coulomb's law. So for the Coulomb's law, so for the F, so that actually equals to, or the proportional to the charge, and reversely proportional to the R square, to the distance. So this is something that you should be very familiar with. Then in this case, when we apply this, and then we needed to find out the charge and the basically the size of the distance. So if we compare these two items and we check, we know actually they belong to the same group. Both of them are 2A group. So if you check the periodical table, so we needed to look at on the side. So then you are going to find out both of them are the second group, but the strontium is well, basically is at the bottom. So we know the trend of the periodical table from the top to the bottom of the periodical table. The size, the radius of the molecules, the radius of the atom will increase. So because of the increase number of the shells. So then here, we know that the strontium will have the larger size than the magnesium. So then let's come back to see the what we have here. Then if we compare the charge, we know both of them has a 2+ charge. So basically the charge will be similar. However, the size is different. So the first one, the magnesium, will have a smaller size. And so the smaller size will, that correspondent to the higher electrostatic force. And so that also corresponded to the higher lattice energy. So that has been verified by the experimental data provided by the on the table. Yeah, so this question actually is to check your understanding of the understanding of the periodical table and the periodicity of the atoms, but they ask in a in a different way. Okay, so this is question 6. And the next one. The last one is some kind of like electrochemistry and redox reactions. This is a little bit of combination of both of them. Okay. So here, in order to determine the concentration of hydrogen peroxide, and in the solutions, we'll basically they propose two different kind of the experiments by using the so this one is using the titration method to determine the concentration. So by the way, the titration method is a very important quantitative method used to determine the unknown concentrations. So here you can choose either use dichromate as a titrant. So it gives you the reactions. And also can using the cobalt as titrant and also give you the reactions, and also giving you a table of the E values for the half reactions. So this is in a, basically this is the reduction potential. This is a very standard potential way to give you the potentials. So no matter how the reaction is, the reduction potential is always like here you have the species and then plus the electrons and then give you the product and then give you the potential. So this is the reduction potential, and also this is the potential you can typically check or get from the handbook of from test like this. However, you should know how to use them correctly, because this is only tell you the reduction. Well, basically, you don't know what is oxidation. Well, oxidation actually is just a reverse it. So, because of this reason, when you are giving chemical reactions, you need to figure out for these pairs which one is reduction and which one is oxidation. And through that one, you can find out the information that you need. And typically, and for the potential of the reaction cell, so that equals to the reduction potential of the cathode minus reduction potential of anode. And then we know that cathode is related with a reduction reaction, and the anode is having a oxidation reactions. Okay, so now let's have a look what happens here. So for question A, find out the cell potential between the dichromate, using the dichromate as a titrant. So let's check the first equations. So if you use a dichromate, the reaction is, well, basically here you have dichromate, and the as a reactant, the product will be the chromic ions. So basically you have this pair. And for the hydrogen peroxide, so that is between hydrogen peroxide and oxygen. So this is another pair. So from here, you know that if you check the half cell reactions, so that correspondent to the this reaction and also H2O2. Also the last reactions. So because so that is determined by the species involved in the reaction. So here you have hydrogen, H2O2, and oxygen. If you check the other one, so this is H2O2 with water, so it's different. So basically, you are going to use the last two equations for the first scenario for this equation involved the dichromate, and then in this case we need to check which pair is which pair have the reduction reaction and then which pair have the oxidation reactions. So we know that dichromate will actually has reduction reactions. So that equals to 1.33. So this is a dichromate, and the minus the anode or the oxidation reaction. So that is 0.7. So minus 0.7, it gives you 0.63 volt. So this is E for the first reactions. And for the second part, that is happens between the pair between the cobalt and the hydrogen peroxide. So we are going to analyze in the same way. For the cobalt, so that is the change between the CO2 plus and to CO3 plus. I change a different color. So this is a first pair, and hydrogen peroxide and water is the second pair. So then in this case, we need to check which one has a reduction and which one has oxidation. So, or in another word, for the half reactions, we are going to use the first two pair. And we know that for the hydrogen peroxide, it changed to water. Well, basically, this is a pair that have the reduction reactions. So because this is the same as a reduction pair, so here we can find out the ratio is 1.77, and then minus the anode is the other way. So you can see that the change here is a cobalt 2 plus to cobalt 3 plus, CO3 plus. Basically, that is the reaction in the reverse order. So in this case, you need to, well, basically, this is the reason why here you have a minus. So that is 1.84. So that gives you minus 0.07 volt. Okay, so basically in these two, if you compare these two E, and then you should tell which one could happen or which spontaneously happen, and then which one could not. So well, basically it favors the cell that has the positive numbers. So then in this case, that is the answer for the second question. Based on the E values and choose a titrant for this experiment. So then in this case, for question B, we needed to choose the first one. We needed to choose dichromate because from the calculation, the dichromate give you the positive potentials. So we choose dichromate. Okay. So that is because the delta E of dichromate is positive, and then this is thermodynamically favorable. And for the second part, calculate delta G. Well, so this one you needed to know the relationship between delta G and the E. So that is minus NF E0. And N is the number of the electrons transferred in this process. So then you can check how many numbers of the electrons has been transferred. So in this reaction, we know that dichromate is positive 6, the oxidation number, and changed to positive 3. So for each of the chromate, the change is 3 electrons. However, here, because you have dichromate, so here you have 2. So then you need to have like 3 times 2, that equals to 6. So the total electron transferred equals to 6. And the F is a Faraday constant. So you just put in the constant here. And then times the E, the cell potentials. So that equals to 0.63. And then give you the reading of minus joule. So and then you can convert it to the kilojoule. So that is minus 364 kilojoule per mole. So from this calculation, then you can see that the delta G is smaller than 0. So basically, that also confirm this is a thermodynamically favorable reactions by using the dichromate as a titrant. Okay. Yeah. So this is question 7. I believe this is the last question that in this set of the test. Yeah. So electrochemistry is not covered in the AP exam, but I think it's still good for you to know to know this point, because the topic covered by this question is the most fundamental questions for the AP test. Okay. I think probably today we just stop here. And the next time I'm going to go over the topic of equilibrium, and also also the diagnostic test that I sent it to you yesterday. So then we are going to, I think we are going to do more exercise and then get more familiar with the key topics. Okay, so then thank you for your time this afternoon. I think we will just stop here.